Hey everybody, today we're going to learn triangle properties lesson number 3. We're going to talk about perpendicular bisectors and we're going to talk about angle bisectors, and there is a whole lot that goes into this. You may have a note sheet that has those 3 triangles filled in. You may have a note sheet that does not have those 3 triangles filled in. Doesn't really matter. It's a time saver for sure, but the most important thing is that we get the practice in. So if you do not have those 3 triangles filled in, take a second and do it and pause the video. In the meantime, we are going to practice drawing perpendicular bisectors and make some conclusions. Now, hopefully you learned this already. In order to be a perpendicular bisector, it has to be perpendicular and bisecting. Now, whenever it comes time to draw a perpendicular bisector, you should be grateful when you see a horizontal line, because what's perpendicular to a horizontal line? Well, it's got to be a vertical line. So the easiest way to take care of this first perpendicular bisector that I'm going to draw is just to draw a vertical line that goes through the midpoint of the bottom. So essentially I just did some counting here. If I'm going a total distance of 8, and I wanted to bisect that segment, then I would have to go 4 on each side. I went to the midpoint of the segment. That's what it means to be bisecting. You have to cut it in half. So that's where you end up. Now, in and of itself, that doesn't look like much. We do know that it's perpendicular because a vertical line is perpendicular to a horizontal line. But in and of itself, like I said, that doesn't mean a whole lot. Now, to make the next one, we go to the next midpoint, and I think at this point most of you can pretty much just eyeball it and make a good guess. I can say that if we're looking at a total of going up 8 and over 4, then halfway would be up 4 and over 2. So that's one way of figuring it out, but there are a lot of different ways. Now from here, there are 2 different ways to make a perpendicular bisector. You can either rotate your paper around and then just draw a line straight up, turn AB into the base and then just draw a line straight up, or you can base it on slope. Now, the slope idea is basically saying, hey, the slope of this line, we already talked about it, 8 over 4, 4 over 2, that's the same as 2 over 1. If you had a slope of 2 and you wanted a new perpendicular slope, you would flip it and change the sign and you would get -1/2. So you have 2 choices here. You can either turn your paper around and rotate it until you have AB on the bottom and then just draw a line straight up, or you can think of it in terms of slope. Either way, I don't really care. If you do it the slope way, then what you should notice about what I just did is that the line that I just made is perpendicular to the side, because it has an opposite reciprocal slope. That's how perpendicular slopes work. Okay, so you can either rotate your paper around and draw a straight line or use slope. Either way is fine with me. So depending on which way you do it, you can either, once again, when you get your third one, go with slope, or you can just turn your paper around until BC is on the bottom and then rotate from there. What you should end up with when it's all said and done is a third perpendicular bisector. No matter how you chose to draw it, that shouldn't really be an issue, but your third perpendicular bisector should look something like this. Now at this point, I think it's actually pretty amazing when you look at it. All 3 of the perpendicular bisectors came together at the exact same place. All 3 of them are touching at the exact same spot. So we have 3 perpendicular bisectors. They are perpendicular and bisecting. And they all ended up touching at the same place. Okay, so we have perpendicular and we have bisecting, which means this is the same distance as this. This is the same distance as this. And we already had the first one. Now, here's what's hidden behind all of this. It turns out that if we were to try and draw a circle and that circle were to go around and touch all three of the endpoints of the triangle sides, so all three of the vertices there, it turns out that circle that you draw, this is where it gets really super crazy. That circle that you draw, look at where the center of that circle would be. The center of that circle would be at that point where everything came together. So to me, it's just the way all of this fits together is just absolutely crazy. But there's a lot of value in figuring those things out. So perpendicular bisectors have a lot to them. It's not just, hey, we're going to draw this line that's perpendicular and bisecting. There's a lot of math that fits into it and a lot of really cool designs. They look kind of Da Vinci-ish when they're all said and done. Let's try the second one because it's going to apply. That same exact technique that we just did is going to apply to the second one as well. You just might not expect it. So I'm looking down here, and this thing has a total length of 10, so I'm going to go 5 and 5. I'm going to break this up into 2 equal pieces, right here and right here. Right triangles are the best ones to deal with. So in case you didn't pick up on that, the first example that we did worked out the way that it did because it was an acute triangle. This next one is a right triangle, and it's going to work out a little bit differently. So we have a right triangle. If you try to do a perpendicular bisector and make it perpendicular and bisecting, you've got a horizontal line, so I can make a vertical line to be perpendicular. Now, the reason I like dealing with the right triangles is because now we also have a vertical line, and what's perpendicular to a vertical line? Well, it's going to be a horizontal line. So the second perpendicular bisector is actually also super easy to draw, and we only have one more to go. Now again, you can either look at it in terms of slope, or you can just rotate your paper until DF is the base, and then just draw a line straight up. That makes your life really easy when you're dealing with perpendicular bisectors. If you're going to turn it into a slope conversation, the slope of DF is -1. So if I wanted a new perpendicular slope, that would change to +1. So I am going to start on the third midpoint, which is going to be right here, and then I'm going to go up 1 over 1 from there. Now, again, if you just rotate your paper instead, you'll get the same results, and that would be totally fine. Obviously, that didn't really cut through our triangle very well, so instead of going up and to the right, I'm going to go down and to the left, and I have my third perpendicular bisector. And you probably expected it. Sure enough, look at that. They all came together at exactly the same point. Now this time, what was weird about that point was instead of the point being on the inside of the triangle, that point was actually on the triangle itself. It actually landed right in the middle of the hypotenuse of the right triangle. So I thought that was pretty weird too. Now that circle trick, this is where it's going to get super wild. And I say that it's going to get super wild here because now, if you were to try and draw a circle that touched every single last corner, that circle would actually end up being way over here. Whoa. Now, that being said, take a look. What's the center of the circle? It's where the 3 perpendicular bisectors touched. So even though our drawing was completely different, the same rule ended up showing up again. All right, we're going to do one more example of this. This one is with an obtuse triangle. And you need to pay close attention to this. This is usually the one that kids get wrong. It's not any fault of their own. It's just the way that it works. Now, we've got ourselves 3 midpoints. I'll just put them all in red for now, and I'll go over them again here in a second. Those are my 3 midpoints. Again, you can just count squares if you want. I'm not going to end up trying to do any sort of formula with it. Perpendicular to a horizontal line is a vertical line, so the first perpendicular bisector should be really easy to draw. Now, I'm going to tell you right now, draw this one a long way because something extra special is about to happen, and special might not be the right word for it. It's actually kind of weird, but you'll see what I'm talking about here in a second. So that line that we just drew, it is perpendicular, it is bisecting right there. The second perpendicular bisector, this side has a slope of -1. If you were to go from x to y, you'd have to go down 4 over 4. That is a slope of -1. If I want to change that and make a new perpendicular slope, I would have to change it to a +1. So that means my perpendicular bisector is going to take this point and it's going to go up 1 over 1 from that point. And it's going to keep going like that. And remember, if you want to go, instead of up and to the right, you're allowed to go down and to the left, and it would look kind of like that. So this is where we run into that first moment where we're like, wait a second, something strange just happened. They crossed each other. The red line and the blue line, they crossed each other, but they crossed way out in outer space. They crossed outside of the triangle. That was actually supposed to happen. And we'll get into that here in just a second. The third perpendicular bisector, the slopes are getting a little bit more difficult to deal with here. So at this point, you might want to just turn your paper over until XZ is the base and then just draw your line straight up. But if you want to do it based on slope, this line has a slope of -2 over 5. Again, I told you the slope thing is going to be kind of weird. If you want a new perpendicular slope, it would end up being 5 over 2. So I need to draw a line that has a slope of +5 over 2, up 5 over 2. Turns out it's actually not that hard to find because that should put you exactly where it was supposed to. It should put you right at that place where all 3 of them cross. So sure enough, we do have a location, the location where all 3 of them crossed. Which brings us to one last thing. We talked about the circle trick. Sure enough, the circle trick also works here. You wouldn't necessarily expect the circle trick to work on a triangle this big, but it does. It's actually going to cut off from the video because our picture is going to be so strange looking. So you might not even be able to see all of it because it cuts off. But that is the deal. Here, I'll just show it to you real quick just for a second. This circle should be way out in outer space, which is okay. That's what it was supposed to do. In fact, that's actually the pattern here. If your triangle is acute, the place where they all meet up should be inside the triangle, which in this case is 0, -1. In the right triangle, the place where they meet up should actually be on the triangle itself, which in this case was -1, 1. And if your triangle is obtuse, the place that they meet up is actually way out in outer space. In this case, it was at 3, 3. So that is not a coincidence. None of the things that just happened are coincidence. All right, let's get to the theorem involved here. It is the concurrency, and being concurrent, when you concur, you agree with someone. So concurrency is just where they agree. It's where they touch. The perpendicular bisectors of the sides of a triangle are concurrent, so as in they hit the same place at a point equidistant from the vertices. As in the distance, if we go back to that first picture, the distance from here to here is the same as the distance from here to here and the distance from here to here. which makes sense because if we're thinking in terms of a circle, that line that I'm drawing right now is a radius. And no matter where you go on a circle, the radius should always be the same distance. All right, let's talk about what this means to us here. That was a whole lot of information. The point where all the perpendicular bisectors meet is called the circumcenter. We just talked about it. That point is the same distance away from every vertex of the triangle. And then we get back to the vocab. The reason this is called a circumcenter is because if you circumscribed a circle around the triangle, that's the key here, is around the triangle, that point would be the center. So that magical point where all three of the perpendicular bisectors came together, that point was always the center of the circle that we drew. Okay, so that's the value of it. All right, real quick, let's try to bisect the angles instead of the sides. We're going to take that first triangle here that we used earlier, the -4, -4, 0, 4, and 4, -4. We don't have to spend a lot of time sketching this one out. It's actually the same as what we had on the first one. And I want to show you how angle bisectors work. Now, angle bisectors are definitely going to be much more of a guessing game. And the reason they're going to be more of a guessing game is because even if you have a protractor, it's not going to be very easy for you to take an angle and chop it in half. However, that being said, I mean, you should be able to eyeball it fairly well. You should be able to have a pretty good idea of what's being cut in half and what's not. So what I want you to do, use your best estimates, and I want you to take every angle, and I want you to start where the angle starts, and then just draw a ray that just cuts through it. And do your best to try to create a ray that chops every angle exactly in half. Now, obviously, one of them is going to be super easy because if you were to take the top and you wanted to cut the angle straight in half, you could just draw a line straight down or draw a ray straight down. The other two are going to have to be your best estimate. If you're off by a couple of degrees, it's okay. But like this green line right here, that is not an angle bisector. This is not an angle bisector. If you want it to be an angle bisector, you have to do your best to chop the angle directly in half. Okay, so it should look like that. Okay, so we got that and that. And then we already know that that top one chopped the angle in half. Now, believe it or not, surprise, surprise, look at that. All three of them touched at the same place once again. There is some relevance to that one too. Before I get there, let's get our last theorem out of the way. The last theorem is going to be the concurrency of angle bisectors theorem. You may have to write small on this one because it got crunched for space. It's okay, you may need to draw a third line, it's not a big deal. The bisectors of the angles of a triangle are concurrent at a point equidistant. So once again, we're talking equal distance from the sides of the triangle. So let's talk about what that means. With perpendicular bisectors, we used a circle to describe it. We drew a circle that went around all three vertices, and we used that to describe the theorem. So this time around, we're going to do the same thing, but what we're going to do this time is instead of drawing the circle around, we're actually going to draw the circle inside. There you go. That's where it gets a little bit crazy here. And sure enough, the distance from here to a side is going to be the same as the distance here, which is going to be the same as the distance here. Once again, we're talking about a radius. Looks like a ticking clock here. So whenever you're building a circle outside of a triangle, you can use the perpendicular bisectors. If you're trying to build your circle inside the triangle, then you're going to use angle bisectors. So a little more vocab and then we can quit. The point where the angle bisectors come together is called the incenter. And the reason it's called the incenter is because a circle that barely touches each side could be inscribed. So instead of circumscribed, which means you go around, now we're calling it inscribed, which means we're going on the inside. So there was a whole lot of information there. I'm sorry it went long, but I hope that helped you out, and I will see you next time.